Chapter 6 in class exercise 2 method of sections. Question 6.32. Determine the force in the members EI and GI of the truss which serves to support the deck of a bridge. State if these members are in tension or compression. So for this problem, we need to calculate the forces into the members EI, which is this, and Ji, which is here. So we need to calculate forces only in these two members, and we need to state if those members are in tension or compression. And for this purpose, we will use method of section, because if we use method of joints, then we have to solve for all the previous joints before we even solve for the joints where these two members are connected to. Now to save time, we will use method of section. So first step is we would like to calculate the support reactions at joint G, and then we will take the cross section. Okay, so here are the steps for method of section. Step number 1, label all the joints and supports. Treating the entire truss structure as a rigid body, draw a free body diagram and apply equations of equilibrium to solve for unknown support reactions. Draw a section line that passes through the members that you are trying to solve for the forces in. Section line doesn't need to be a straight line. Consider one of the sides of the section and expose the internal forces. For the free body diagram of the section, consider the external forces, support reactions, and exposed internal forces. Apply equations of equilibrium to that side of the section and solve for unknown. So let's follow the steps. Step number 1, define the support reactions. So G is a type of rocker support which allows motion in x direction, but it prevents the translation in y direction. So it has only one support reaction, which is vertical. Support A has prevents both x and y translation because it's the type of pin support. So it has two support reactions, AX and AY. So here are the support reactions that are being drawn. GY, by the way, this is the final answer. We don't know the magnitude of GY as of now. So let's say GY is vertical, AY is vertical, and AX is horizontal. Now to calculate GY, we need to, because we have three unknowns here, AX, AY, and GY. Now when we take the cross section, we should have some idea about what side of the section we would like to keep. And for this problem, we would like to keep the right side of the section because there are fewer forces. So we will discard the left side. That means we will not need to know AX and AY. So we can apply the sum of moments equation at A. So when you apply sum of moments at A for the entire truss equal to 0, counterclockwise is positive. We need to include the moment because of 4,000, 8,000, and 5,000 newtons about A, and their distances are given here. So and they all are clockwise, so negative. So 4,000 multiplied by 9 minus 8,000 multiplied by 18 minus 5,000 multiplied by 45. Now moment of GY about A is counterclockwise. See this counterclockwise motion here? So that's positive. So it's GY multiplied by its distance is 36 feet equal to 0. So from that we can solve for GY support reaction, that is 7,500 pound, and that's positive, means the assumption of GY vertical is up. So that's why I have this answer here like 7,500 pound. So that's how it's being calculated. So to calculate this support reaction, we have applied the sum of moments equation at A. So we don't need to know the value of AX and AY's moment about A, because those moments are 0, because there is no perpendicular distance. We only included the moment of 4,000, 8,000, 5,000 and GY about A. Now the next step is to take the cross section, and because these two members are oriented in such a way that we cannot take a straight line section that passes through both EI and JI, we will take a section which is a curved, it's a curvature such as shown here. So our section is this red curve that goes to our members of interest EI and JI. It also cuts the member EF So we will expose that member also. So when we take the section, we would like to make sure that it does not pass through more than three members, because all the members that it pass through are unknown. So if we have more than three unknowns, we cannot solve it because we have only three equations of equilibrium. So once we take the section, then we will keep only the left side of the section. Everything which is left of this like red curve here, everything on the right of the red curve, that we will keep, and we will, for temporarily, we will not consider the left side of the red section. So this is how the section looks. And because after taking the section, we are exposing the internal forces. So if the internal force goes into the member, then we assume that the member is in compression. So we are assuming that Fji is in compression, Fei is in compression, but Fej is in compression, Fei is in compression, but Fji is in tension because the arrow is coming out from the member. Okay, and now even though we have taken the cross section, we can still extend these two lines, and this point is E that we have here, this E. Okay, so because that's still the point which is connected to both of these members, I have extended them, and that's the point where they meet at E. So we have three unknowns. This is our new problem. So we have three unknowns: Fej, Fei, and Fji, and the externally applied force is 5,000 Newton, and support reaction is 7,500 Newton. And now we can solve for these three unknowns using our three equations of equilibrium. So first thing that we can do is we can apply the sum of moments equation at E. Even though E is not on the right side of the section, we can still write the equation of moment at E, because these two members they meet at E. So when we do that, we don't need to consider the moment because of Fei and Fej, because those two forces do not result in any moment at E, because there is no perpendicular distance. So the moment we need to include is because of Ej about E. So Fej multiplied by perpendicular distance, which is this 12 feet, and that's clockwise, so it's negative. Sum of moment of this 5,000 Newton about E, which is 5,000 multiplied by 9, perpendicular distance from the point of interest, clockwise, so it's negative, and 7,500 multiplied by 18, and the distance from E is like 18, and that's counterclockwise, so that's positive. And if this whole structure truss is in equilibrium, then sum of those moments is 0. So let's apply that equation. Sigma m at E equals 0. Counterclockwise is positive. So it's minus F Ji times 12 minus 5,000 times 9 plus 7,500 times 18. This 7,500 is Gy here, equals 0. So from this we can solve for Fji, which is 7,500 pound, or we can write this as 7.5 kilopound, where kilo is 10 to the power 3. And we get the positive answer. That means this assumption of arrow coming out from the cut member is the correct assumption. So this member is in tension. So we write in bracket T for tension. And now the only force that we need to solve for is force EI, which is this. So we can apply sum of forces in vertical direction and solve for this, because the vertical unknown is only one, thus, while the 5,000 and 7,500 are known forces. So applying sigma Fy equal to 0 for this side of the section, you can say that 7,500 is positive, that's Gy, minus 5,000, that is externally applied load, minus Fei is equal to 0. It's negative because it's going down. So for sigma F, going up is positive, sigma Fy. And from this we can calculate Fei as 2,500 pound or 2.5 kilopound. And we get the answer that's also like the positive number here. So what it means that this assumption of this arrow going into the member is correct. That means member EI is in compression. So we write in brackets C. Okay, so that's how we use method of section. So once again, quick recap of how we solve this is first we label all the joints and supports, so such as A, B, C, D, E, F, G, and then all this like remaining joints. Then for the entire truss, we calculated the support reaction. So we have calculated support reaction at Gy by applying this equation for the entire truss. Then draw a section. So we have drawn a section using this red curve here. And then we kept the right side of the section and exposed the internal forces from the members that the section line passed through. Now, once again, quick recap of if we when we expose the internal forces and arrow goes into the member, that means the member is in compression. This is what we are assuming. But when we expose the internal forces and arrow leaves the member, we are assuming that the member is in tension. So we have assumed that these two members are in compression and this member is in tension. And then for those exposed forces, we have applied once again equations of equilibrium and solve for the unknown. Okay, thank you.